Before we get started with today's lecture, let's look at what we did last time, in which we looked at two applications of quantum information. One is quantum lithography. In quantum lithography, one utilizes this what's called the Hongo-Mandel effect. In the Hongo-Mandel effect, we have these two photons coming at a beam splitter, getting bunched and then going either in this direction or in that direction, and using such a state, we saw that one can write a pattern on a substrate which is twice as dense as one would be able to write with a single photon state or just a classical light with same wavelength. So here we have, this is the pattern, this one is a pattern we can write if we have a classical light of wavelength lambda, but this is the pattern that we can write if we have the two photon entangled state with each photon being at wavelength lambda. So with the same wavelength, but it being a two photon state, one can write on the substrate a pattern which is twice as dense. And so this way, if one has an n photon entangled state, then that would provide an n-fold lithographic resolution enhancement. So that's a very that could be a very useful application of such quantum states. So that's one application we looked at last time. The other application we looked at was quantum cryptography. In quantum cryptography, we looked at two separate protocols. One is BB84 protocol, the other one is called Eckert protocol. BB84 protocol only requires single photon, single qubit states in polarization, while Eckert protocol requires two photon entangled in polarization degree of freedom. Both these protocols are very similar. This protocol has some benefits to it, some advantages, but we did not go through those. The way we presented was pretty much we presented both these protocols at pretty much the same footing. So the way both these protocol work is that first it involves what's called the distribution of a raw key, in which Alice sends a qubit or a string of qubits to Bob, and similarly in Eckert protocol, the source sends out an entangled pair of qubits to Alice and Bob, and then Alice makes a measurement on that qubit, and that making a measurement by Alice on the qubit is equivalent to Alice sending qubits to Bob here. So the distribution of a raw key in quantum cryptography, either in BB84 or Eckert protocol, requires Alice to choose a basis randomly, either between horizontal vertical or diagonal anti-diagonal. So in BB84, Alice will choose a basis and send the photon in that basis. In the Eckert protocol, Alice will make a measurement by deciding either HB or DA as the measurement basis. So these are the example that I've discussed. These are the bases decided by Alice randomly, DA or HB in different instances. And for each basis, and then these were the bits that Alice decided to send. So for example, in this one, the one means that Alice in this case decided to send anti-diagonal photon. In this one, Alice decided to send a horizontally polarized photon, and so on. And these were the measurement bases that Bob chose, and again randomly and without completely and not knowing what was Alice's choice of basis. So these were the Bob's random choice of basis in each instance, and these were the bits that Bob then observed. So this was the distribution of raw key step. The next step in quantum cryptography is what's called basis reconciliation. In this step, Alice and Bob then compares that in each instance what basis Alice and Bob happen to choose. So if after comparing the basis, again they only compare the basis and not the bits. So after comparing the basis, if they find that in a particular instance they happen to choose different bases, then they reject those instances, and only in the instances when they happen to choose the same basis, they keep those measurement results. And when they choose the same basis, then of course their measurement results will be completely perfectly correlated, and here at the end of it they generate this key 0011 that they both will then share. So of course these two, the string of key 0011 will be exactly the same, because in this case these are all correlated results, and this is called shifted bits. These two strings of keys will be exactly the same if there is no eavesdropper, but if there is an eavesdropper, that means there is an effort in which one tries to get information from this, either by making a clone of it or by doing some other measurement, then that effort will actually disturb the quantum state here, and that will then cause error in this bits. So next step in the cryptography is that estimation of that error and then correcting for that error, and then something also called the privacy amplification. Of course, we didn't go through these steps because this is common in even classical cryptography schemes. And these two are what's completely quantum in this quantum cryptography. Now, this is perfectly secure quantum cryptography because of the laws of quantum mechanics. We discussed those laws. But essentially the thing is that if somebody, if an Eve makes a measurement, then Alice and Bob would actually get to know by seeing the error in their shifted bits. So if the shifted bits has no error or is less than some threshold, that means there has not been eavesdropping effort. But if the error is more than some certain threshold value, then that means there has been an eavesdropping on those cryptographic protocol. And then Alice and Bob will then discard that and go to the next effort. So that's how quantum cryptography is perfectly secure. Now we are going to look at one more application of quantum information, which is quantum teleportation. In quantum teleportation, one tries to send a quantum state without sending the system itself. So here we have a particle C, the state of which is phi. One doesn't know what the state is, but then one wants to send this state of particle C to the state of particle B. And that is the aim of the teleportation. Again, when we say teleportation, it is teleporting a quantum state and not the quantum system. The way to understand this is through kind of this cartoon. And here we have, let's say, these two particles. We want to teleport a state, and let's say let's say the smile let's compare the smile to the quantum state. And then what we do in teleportation is essentially just teleport this smile. So after teleportation has the exact same smile, and then we say the teleportation is complete. So in quantum teleportation, we have these two particles A and B, and they share a pair of entangled photons in the polarization basis. This is Alice, this is Bob. Alice has another particle C, and state of that is phi. And so aim here is that Alice wants to send this state phi without actually knowing the state and without actually sending the particle C. Alice just wants to teleport this state phi of particle C to the state of this particle that Bob has. So of course Bob's particle has some state over here after down conversion, but then Bob will make some unitary transformation, and after which the state should become exactly that of the particle C. So that is the aim here. So now let's see how this is done. So in teleportation, of course, Alice and Bob, they share an entangled state, and of course they can share any of the four polarization Bell states. These are all maximally entangled state. There could be four of them. They are all orthogonal to each other, and these are called polarization Bell states. For example, phi plus is HH plus VV, phi minus is HH minus VV, psi plus is HV plus VH, and psi minus is HV minus VH. So these are the four polarization Bell states, and there are techniques for measuring different Bell states. For example, we have a particle B, and so there are techniques by which one can actually find out whether these two particles are in state phi plus, phi minus, or psi plus, psi minus, and so on. And this technique is referred to as Bell state measurement technique. In fact, we are going to use this Bell state measurement technique as part of the teleportation scheme. So essentially in the Bell state measurement, given any two particle, the one can find out as to which Bell state the two particles are in. Okay, so with that, let's start with the teleportation protocol. So here we have Alice and Bob sharing an entangled state, and here we are showing PDC. Maybe that's just one example where these photons can come from. So Alice and Bob share this particular polarization entangled state HVVH. That is the psi minus. Of course, Alice and Bob, they do know which entangled state they are sharing, but this teleportation protocol that we are going to do now, which was first proposed in this paper, can actually work with any of the four entangled polarization Bell state, but we'll show it with this particular polarization state. Okay, so that's the state that Alice and Bob share. Alice also has another particle C, and C wants to send this state phi to particle B. Now the state of particle C is the alpha H plus beta V. Of course, Alice has no idea as to what are the values of alpha and beta, but so without knowing the state itself, Alice just wants to teleport the state. So this phi C we can write as alpha 10, beta 01, and so in the column vector form we can just write it as alpha beta. So that's an unknown state that this particle C has. And this, the particle A and B, that is Alice and Bob, they share an entangled state. So that's a two particle state. This we know that which particular state they are sharing, but this one, the state of particle C, that we don't know. Of course, alpha square plus beta square is equal to 1. So the joint state of this two entangled particle and particle C. So this joint three particle state. So Alice and Bob are sharing this two particle, and then we have this third particle. So joint state of this three particle, two entangled particle and particle C, is basically the tensor product of this psi minus AB times phi C. So that's just simply the tensor product. And so we can just write it as this quantity over here, that is this state, times this alpha HC plus beta VC. So that's the joint three particle state that we have here. We can write this as, this is two terms here times two terms here. So we can open it and then write it like this. So this joint state of the three particle is HHV alpha minus alpha VHH plus beta by root 2 HVV plus beta by root 2 VVH. And here the way we have arranged is ACB, particle A, particle C, particle B. This is just a tensor product. We could have written as ABC as well. Okay, so that's the joint state of these three particles. So now the situation is Alice has two particles, particle A and the particle C, of course. And now in the teleportation scheme, next C needs to see or find out which Bell state her two particles are in. That means what is the Bell state that the joint state of these two particles A and C, what is the Bell state that they are in. So that is the Bell state measurement now C needs to make. So before we see how C makes that measurement, let's just see that Bell basis representing particle A and particle C, that we can write as phi plus minus AC, psi plus minus AC. This is same as the Bell state we wrote earlier for particle AB. So phi plus minus is HH plus minus VV, psi plus minus is HV plus minus VH. So these are the four Bell polarization Bell states corresponding to particles A and C. Okay, so that's the joint state that we can have in principle. And now if that's the joint state, then one can write this HH in terms of, or VV in terms of this phi plus minus and psi plus minus. So we can just invert these four equations, and then we can actually, this can be easily shown that HH is equal to 1 over root 2 phi plus phi minus, VH is equal to 1 over root 2 psi plus minus psi minus, HV is 1 over root 2 psi plus psi minus, and VV is equal to 1 over root 2 phi plus minus phi minus. Okay, so these are the Bell states, polarization Bell states corresponding to particle AC, and so the basis vectors in the polarization basis of particle A and B, HH, VH, HV, VV, that can be written in terms of the polarization basis, polarization Bell states like this. So now that we have this, we can write the joint state of three particles. We can just rewrite the joint state of three particles in this manner, and this will help us with the teleportation. So the joint state that we have written like this here has HH for AC and then V for B, VH for AC and H for B, and so on. And now we know that how we can write HH in terms of the Bell states for particle AC. So let's write it here. So this HH we are writing phi plus AC, phi minus AC, and this 1 over root 2 multiplied with 1 over root 2 gives us alpha by 2 over here, and VB that remains as is. Next step, next term is alpha by root 2 VH. So this VH we substitute from here, that is psi plus minus psi minus, and again this is root 2 and that's root 2, becomes alpha by root 2. And similarly we write the other two terms by substituting for HV and then VV. So this is the joint state of the three particle that we can rewrite like this, and here we are writing it in terms of the polarization vectors for particle B and polarization Bell states for particle A and C. Okay, so we have the phi plus, phi minus, psi plus, psi minus as the polarization Bell states. So let's rearrange this equation one more time, and let's collect all the coefficients we have with phi plus, phi minus, psi plus, psi minus, and so on. So let's first do it for phi plus. So with phi plus, we have phi plus AC, we have this VB from here with alpha, and 1 over 2 comes over here, and then we have another phi plus over there, and that has a HB with a beta by 2. So, we have HB with a beta and then 1 over 2 here. So, we have 1 over we have half phi plus for AC and alpha VB minus beta HB. So, that is the state of the particle B, and that is the state of particle AC. Similarly, we can collect the terms containing phi minus and then write it like half phi minus for AC and times tensor product alpha VB plus beta HB. And similarly, we can do it for the other two terms as well by collecting the terms containing psi plus and psi minus. So, this is again just rewriting the same 3 particle state, and now we have it in terms of that we have this 3 particle state given by the state of particle AC, that is in terms of the Bell state, times the state of particle B. And then we see that this state contains a superposition of 4 different terms, coherent superposition of 4 different terms. Okay, so now the next step in quantum teleportation is the measurement of the Bell state. So, we have this 3 particle state. Of course, this is a coherent superposition of 4 different terms, and we know that if we make a measurement, then the system will collapse into either this term or that state or that state. So, the system has to collapse into one of these 4 states. And of course, if the system collapses into the first one, we will find that particle A and C are in this Bell state phi plus, and the particle B ends up being this state. If the system collapses into this one, then we will find that the state of particle AC is in this phi minus Bell state, and particle B has this particular state, and so on. So, Alice now makes a Bell state measurement on the state of particle A and C. And of course, if C makes a Bell state measurement, then C will end up with either phi plus, phi minus, psi plus, psi minus. So, let us say that C ends up with this term, that means phi plus AC. That means the state collapses into the first term. So, if the state collapses into the first term, Alice definitely gets phi plus AC, and state of Bob's qubit, that means the state of particle B, that becomes alpha VB minus beta HB. That is the state of particle B. Okay, so that is the state of particle B right over here. We can also write it as minus beta by alpha. Now, Bob makes a unitary transformation on his qubit. So, remember both Alice and Bob, they know which particular Bell state, phi AB or psi AB they started with. So, that knowledge they have. Only thing they don't know as to which state, what is this state phi psi is. Now, after Alice's measurement has yielded this state phi plus, Alice lets Bob know about this information, and this can be done over a classical channel. So, this does not need to be in a secure manner. This could actually be over a public channel or classical channel. So, once Bob gets to know that Alice has, in that particular measurement, Alice has found the joint state to be in phi plus, then Bob will make this unitary transformation on his qubit, which at this point is minus beta by alpha. So, he will make this unitary transformation U phi plus corresponding to this one, which is 0 0 1 minus 1. And if Bob makes this transformation, then we see that the state of Bob's qubit becomes this unitary transformation acting on this state minus beta alpha, and then that becomes alpha beta. So, this state is same as the state of particle C that we started with, alpha beta. And so, the teleportation is complete, at least for this measurement result. So, since Alice and Bob, they both know what entangled state they share here, and so after doing the Bell state measurement, if Alice finds that in a particular measurement she has found the Bell state of particle AC to be phi plus, then Bob will use this particular unitary transformation on his qubit, and then he can be sure that after the unitary transformation, the state that he has it over here is basically alpha beta, which is the same as the state C. Again, Bob and Alice, they both don't know what are the values of alpha beta, but they know for sure that whatever alpha beta Bob gets after the unitary transformation is same as that of state of particle C. Now, let us say if the Bell state measurement yielded phi minus, then of course, the state of the particle B, that is the Bob's qubit, is alpha VB plus beta HB. Now, in this case, the unitary transformation that Bob will make is this U phi minus, that is 0 0 1 1, and we see that after the unitary transformation, Bob's qubit becomes this acting on this and this alpha beta, which is same as the state of particle C, hence teleportation successful. Third time, or if Alice now finds that her measurement yields Bell state psi plus, then in that case the state of Bob's qubit is a minus alpha h plus beta v. So in this case, Bob will make this particular unitary transformation 0 0 minus 1 1, and then we can see that the state of Bob's qubit then becomes alpha beta, same as the state of particle C, and thus teleportation successful. And finally, if Alice finds that the Bell state is psi minus, then in this case Bob has to make the unitary transformation 1 1 0 0 1 1, and we can see that with this the state will become alpha beta. In fact, in this case it is the unitary transformation here corresponds to basically doing nothing. This is just a unit matrix. So in each measurement instance, Alice provides that information to Bob as to what Bell state C obtained, and so in that particular measurement instance, Bob chooses the unitary transformation based on the information obtained from Alice, and then in each instance then he can make sure that the state of the particle after the unitary transformation is same as the state of the particle C over here, and then we say that the teleportation is successful. So this is how teleportation works, that here without teleporting the particle or without actually knowing the numbers or obtaining the numbers or obtaining the doing the state tomography, which is a very difficult problem, one basically transmits or teleports this state of a particle C to that of state of particle A. So that's the quantum teleportation. So in quantum information, the teleportation is very useful and has a lot of potential, further potential application, and in fact this was proposed in 1993. A very convincing demonstration of quantum teleportation was demonstrated in 2012, and this was done over like 143 kilometers, and this is the experimental setup. Again, I am not going to go through the details of it, but the basic principle is exactly the same. So that's a BBO crystal, and then we see that the two parties were separated by 143 kilometers, and then one could still teleport the state. So this was a very convincing demonstration of quantum teleportation. So we will stop here for this lecture. Thank you.